Hello, we're going to talk about Bucket Cache, myself and Viplava. This session is divided into two parts. The first part is us doing a little session on BigBucket Cache, Texas edition, even though neither of us are from Texas. And then the second part is Intel talking about an aspect of Bucket Cache. I can talk about it a bit more. So myself and Viplava, we're kind of representing work that's been done by this gentleman, Daniel Paul. He's a performance engineer at HPE. He started playing with Bucket Cache, trying to go really big, and he found lots of issues. And so we had a healthy back and forth. HPE is trying to back Bucket Cache by SSDs, and like lots of SSDs. They want to go big.
Like
Texas style.
He's from Texas.
And then the Intel talk that comes afterwards is talking about backing Bucket Cache with NVRAM. We'll make a start. I think I kind of covered this slide already. So caching, whenever you read in HBase, the data is actually in HDFS, so it'll go to the HBase process and it'll go then pick it up out of HDFS and return it to the client. So there's a bit of I/O there. So when you do a get on HBase, we don't actually read an individual key value or cell from HDFS. We'll actually pull stuff in blocks. And what's a block? A block is one or n, some number of key values. And the block is generally, it's part of the schema, you set what size it is. Generally, the default is 64K. That's a good fat seek to do against the disk. You get a lot of info in the one go. HBase writes H files, and H files are made of these blocks, and then there's different types of blocks. There's blocks for data, there's blocks that have indices in them. So we can find the key values, which block contains a particular key value. So it would be nice if you read, and instead of going to HDFS, you could go to an in-process cache. As you can imagine, things would run faster. By default, HBase has a cache enabled. By default, it's generally it's about 40% of the heap. You can get some stats on it from the UI. It's the hit rate and stuff. If you look here at the block cache section in the UI. So then what's Bucket Cache? Bucket Cache is an alternate, another implementation of cache. And its core is called an engine, and the engine has various implementations. There's you can have this engine. It can do the blocks on heap. It can do the blocks off heap. The blocks can be backed by a file. This is how you get SSDs into the mix. Files can be M-mapped. And the bucket cache was, it makes buckets of fixed size, and when you read the block, you put it into the appropriate bucket. You can figure out how it generally works. It was written originally by Fusion IO's CTO a long time ago. It's been around for a good while. When you deploy bucket cache, it's actually the configuration is particular. We'll still have the LRU block cache. That'll still be in use, and that will be used. In there, we'll put the index blocks and the Bloom filter blocks, the metadata blocks, in essence, and only the data blocks will be kept in the bucket cache. Bucket Cache has been, it's been starting to come on strong, especially in HBase 2.0, where the off-heap read path work actually expects the off-heap bucket cache to be enabled, because it does ref counting against it, so it saves copies. And we're talking about maybe even having the bucket cache enabled by default in 2.0, because especially with the off-heap read path enabled, things are smoother, GC-wise, but they also just run faster. Bucket cache is becoming important because it's sort of become this. It's one gateway for us to be able to make use of the bigger machines, make use of the RAM, make use of the nice SSDs that the HPE people would like to plug in, or when the Intel people talk, it's one way of us getting at NVRAM. So I'll hand the clicker off now to Viplava.
Okay. Thank you, Michael. So as Michael said, the caching is important in general, particularly, as you know, particularly for reads, because, most of the times, it's obvious, but, just wanted to say it anyway. Most of the times you write once, but you read many times. And again, the next point, even though you might have data in like petabytes of data, but still most of the times you have your working set, much less than that. And then there are the hot areas. And typically you cache them, and most of the times you want to serve the request out of that cache. And that's where bucket cache becomes very important. And obviously you could use like multiple things for bucket cache, like as Michael said, you could use RAM, you could use SSD, and you could use disk. But and if you have a lot of money, probably RAM is good. But what we found is the SSD provides the best ops per dollar per figure, essentially. We have done some study last year, and then these are the chart shows what kind of performance SSD provides. Like the RAM is essentially about 50% faster than SSD, but 17 times costlier, so you can imagine. Whereas the hard disk is much cheaper, on the right-hand side, but at the same time, the performance is way lower, 15, 20, less than 20% of SSD. So SSD seems to be the sweet spot for bucket cache. That's why we concentrated our work on SSDs, and we try to use as big an SSD for bucket cache as possible. And the next other point is, I think probably Intel guys will talk about that, the SSD, use of SSDs kind of gets into, like where we could use persistent memory devices without many code changes. So from a performance engineer point of view, like what is the wish list from bucket cache using SSD? So, some of the things are obvious probably, but it's not our observation, so we'll talk about that later. But let's say if I'm doing a lot of random read IOs, so we want a single, cell HBase GET request to generate just one IO to the file, bucket cache file. And then typically the SSDs like 4K aligned IOs. That's what our experience shows. So, and if you misalign a little bit, you pay a big penalty premium, like for 44% if you just miss by 8 bytes, not aligned to 4K boundaries. And then typically, ideally you like to avoid any file system cache and all that stuff. You want to, if possible, try to use a map or direct IO. And I think there is code already available, but it's not really supported by the distros. So we would like to have that as the mainstream thing. And then we would like to use, as Michael mentioned, bucket cache does provide an entry gateway into the big machine resources. And we would like to go as big as possible. We are asking something like 4 terabytes per region server, using SSDs. And then we would like to have multiple file supports for backing the SSD cache. Right now, you can specify only one file, and the idea is that you could have multiple SSDs and doing parallel IOs to multiple SSDs. Right now, we are forced to do a software RAID, just to use multiple SSDs per node. And then ideally, again, we would like to warm up the cache as soon as possible, so that you serve requests as soon as possible. And so we would like to have a very fast prefetch implementation. And then again, similarly, if you want to change hot tables, maybe in a night you will have different tables to load. So you want a fast deallocation you want to switch the cache quickly. So that was generally what we would like to have as a wish list. But what our observations were a little different. We were surprised initially, and that's where we got in touch with Michael and then we worked together. So the first thing is, if you want to study what's going on with Bucket Cache, it was very hard to find the file format information. So there was a lot of effort spent on that, and I have a slide where the format is there. I'm not going to go through all that, but essentially it's just there for your reference. You can go back and use it for your work. And then we noticed that initially, again, we wanted to use big files, and then it was prefetching was not really working with big files greater than 10K blocks, 100K blocks, sorry. And then, as I mentioned, we would like to have single cell HBase GET request to have just one I/O, but we noticed it was generating something like more than 2 I/Os on average. And then the bucket cache is using actually a lot more space, about 50%, 40-50% more than the actual data size. And then what we noticed was, this is by accident, like prefetch is much faster when you start with empty bucket cache instead of, if there is something left over from previous run, etc. And then this is general observation. The last point is general observation. Like, we did a lot of work and we tuned to get maximum performance. And then, but now we started testing latest, HP being a hardware vendor, new servers with a lot of memory, bigger, better processing power. And it's hard to tune. We are getting a little bit issues there, and we are working with the community on that. So again, when we embarked in this, journey, so we had to use some tools. So this is just for your reference. So if at all you are looking at this kind of stuff, what tools could be useful? And the first thing is obviously the HBase charts, but the default charts are typically not really good enough. They are, as an aggregate, they're good, but if you are trying to get into the details, they're not really. So you would like to enable custom charts. You can, for Cloudera, for example, there is a chart library you can pick up, and then per region server you want to you want to chart bucket cache, things like free size, evictions, store file size, etc. And you want to do it per server. And what we noticed is, again, like Java mission control is good in general, and it works out of the box, just exposes HBase metrics. And the advantage is that you can get sub-second samples compared to a minute samples from the distro vendor tools. And then what we found was the trace level logging is very good. Particularly, that's how we found that the prefetch was not working. The default info sometimes just eats away some messages, some error messages. Then again, there is a nice tool from Cloudera Labs. It's called HTrace. Probably some of you know. It basically gives you a holistic view of your request. It starts from the client library, goes to traces Zookeeper, and reason servers and HDFS all. So it's very nice. And the other thing we used was system tab for really file I/O tracings to see what exactly is happening to the bucket cache file. That's how my colleague, he found that there are 2 I/Os going for each request. And then just the plain xdump on bucket cache file helps to just see the performance. This is an example of custom CM charts. I'm not going to go through all of it. There is not much time. But anyway, so this is like you can see it on slides later. But essentially, you can see what kind of things you can track, like block evictions, block cache free, and cache hits, etc. Okay, and this is just, again, my colleague, he put it there because he took some time to trace these bucket cache I/O. So if somebody is interested, this is a small shell script making use of system tab, and it traces all the I/Os. Again, I'm not going to go through it, but it's there for your reference if you want to see what's going on. And this is the same slide, but if you want to see just enhanced version which dumps in hex format. Again, just it's there for your reference. And this is the file format I was talking about. This was very hard to find, so Michael and my colleague Daniel, they put together this slide so that it's useful for community in general. If somebody is looking at the code, this is very useful, I'm sure. Okay, so just for reference. And then, as I said, we found some issues, so we got contact with Michael, and graciously accepted, and then started working on the issues, and then he'll talk about the current status of the issues.
I think yeah, Daniel just went big with the bucket cache, and then he found all this great stuff. And then he also is a meticulous man and dug in, reading loads of hex and figured out some really great stuff. So we fixed some of the stuff, but there's still a load to do. There's an umbrella issue with the general list. I think things like efficiency. Efficiency is a big one. We can work on with bucket cache, get more data into the cache. The stuff we can work on. But we worked on things like just going big. I think our presumptions were hundreds of thousands of blocks, maybe a million. But then when Daniel was doing like big stuff, he was doing like tens of or hundreds of millions of blocks and running into interesting issues in the UI. We were showing you garbage or a rubbish message. So fix some of those. There's an optimization when we read from HDFS, we'll actually read the header of the next block. So then we can save a seek the next time we go. We were actually persisting that into the block cache, the extra header. So just wasting space. And then an optimization done to improve our scans actually made it so that we often we're doing 2 seeks when we should have only been doing one when you were doing a point get. 2 seeks in the cache backed by SSD. This is all the stuff that Daniel found. But there's lots more to fix. Check out the umbrella issue. I think you're finishing with that.
Yeah. So thanks. So basically, with the fixes the community has done, we could get a really good performance. So this is basically the current figures we have, and this is on what HP calls. Excuse me, I got allergy. So basically we produce reference architecture. We're part of a group which produces reference architectures for all various big data ecosystem like Hadoop, Spark, HBase. So that the paper, the link there is actually about HBase performance reference architecture. So again, this reference architecture is slightly different from the traditional architecture. We call it asymmetric architecture. Essentially, we separated out the compute and the storage. The idea is it gives it becomes more elastic. The compute you can scale as you wish. And for the compute tier, essentially, we use something called moonshot cartridges. Some of you might know. They're kind of microservers. But the advantage is that you can pack 45 of them in this 4.3 U box. It's a weird number, but it's a lot of CPU power. So basically, we tested with 5 of those cartridges, and each of cartridges are like CPU. You can see the figures: Intel E3 with 2.9 and 4 cores each. And then they have each of the cartridges has about 32 GB memory, and then it has the SSDs, disk 2, 960 GB SSDs, and then we have a good networking because we separated out the compute and storage, so we had to have 2 10 GB ports essentially. So the testing was done on using YCSB Workload C, which is again 100% reads. So before we started, we tuned all the other stuff, and we got something like 208K per these 5 cartridges. And then after the work, the community has done, we went up to 454K ops. So essentially, we more than doubled the performance using the bucket cache improvements, essentially. So again, roughly this works out. Like again, it's a little bit complex math. It's a 4.3 U's containing 45 cartridges. So if you do all the math, it comes out to be 1 million ops per 1 U rack space, and that's that much performance we can get from out of HBase. So thanks for your patience, and there are a couple of other references on block cache, and then the HBase reference guide. I think that's enough.
Maybe we'll save questions till the end.
And then, probably.
We'll get our Intel brothers and sisters up.
Thank you.
Thank you.
Hello, everyone. I'm Liqi from Intel. Our team at Intel mostly focuses on big data performance and JVM performance. So today I'm going to share some preliminary results and works we have done to see how we can use persistent memory to help HBase to get even faster performance. As the previous speaker already said, that you can get a billion operations per second per U reg. So probably can get more, OK, so legal disclaimer goes really fast. OK. Yeah, that's OK. All right. So think about this from the hardware point of view. If we get all the software works properly and everything works fine, no GC problems, no nothing, and cache is fantastic, what other problems do we have, right? So given that HBase is using this log structured merge tree, we have two level of storage with two distinguished characteristics. One is better addressable, volatile. That means that if the process crashes or there's a power outage, those things in memory is just gone. And then the other part is a relatively slower with large capacity, but it's a block device. So unless you do some magic, you can just get blocks out of it. That's our disk. So those are the problems currently we have, given that the architecture we are using. The first one is that we are actually using disk in a kind of like burst fashion, where most of the time we're sitting idle because our mem store is handling all the updates. And then some of the times when mem store fills up, it starts to flush. And when this flush actually happens, we have a burst in your disk I/O, either in IOPS, because you're flushing a lot of memory at the same time, or in bandwidth. So we're seeing this performance characteristic in runtime where your disk IOPS will be like shoot up in several seconds, sitting idle, shoots up idle, and all the time. This also happens in compaction operations. The second one is the disk bandwidth inflation. Consider this. I have a key value pair, and I put into HBase. How many times has that key value pair needs to be write to disk and bring back to memory? There will be many, many times. And for the write path, that happens when you have a continuous compactions, because you have to bring them back, delete some stuff, write the still alive ones back to disk constantly as long as they're alive. And then for read, we have a relatively small size of cache, and I bring some key value pairs back in, and then I get revected. Then I bring them back again. And plus, since HBase doesn't cache key value pairs specifically, we're caching H-file blocks. So even though some key value pairs wasn't really a hit, but some other key value pairs in that same blocks got a hit, those key value pairs just get a free write into memory. So the last one is the date format changing. Consider the flush and bring back to memory thing. So for write path, we are serializing somehow the map into a sequence of bytes, and we write them to disk. And then when we read them in, we are not necessarily unpacking all the stuff because we're caching blocks, but when we actually get a hit inside a specific block, we're doing linear search inside them. So the last one actually is not a bandwidth per se, but gives a lot of overhead on the CPU cycles. So if finally we're bottlenecking on the CPU, that will be some problems we're facing. All right, so fundamentally, those problems cannot be resolved if we're still using this memory plus disk architecture. Right. So let's say that we're still keeping the architecture and we're trying to address this problem with what we have currently on hand. Right. So for disk write burst in fashion that requires a lot of bandwidth sometimes, we can use faster drives. For example, the PCI Express Drives, SSDs. Somebody call them NVMe, right? But the problem is they're expensive, right? And they're relatively small in size compared to spinning drives. And sometimes they're not fast enough. So the top of the line products currently we have is the from Intel P series, right? You can see the specs. They have 20 microsecond for latency, and memory has relatively 100 nanoseconds. So that's a really large performance gap. So sometimes it's not fast enough. And then for the disk bandwidth, we can have larger DRAM so that we don't flush that often. So we have larger flush files. We compact less. We keep the blocks in the cache for a longer time so that we don't bring them in a lot. The problem is it's even more expensive than the PCI Express drives. And they're smaller compared to the NVMEs, and they're volatile, right? So something that was lost in memory, even though we have the Red Hat logs, we can replay all the stuff, we can refill the cache, but when there's something wrong, those things are gone, so we have to redo something. That's a lot of things we want to do. And data format changing, as long as we're persistent on block device, we don't have problem. We don't have solutions for that. So now the question is, do we really want to do persistence on block device? So previously, we don't have a choice because every persistence device is a block device. So, but just consider this: if we can persist on a better addressable device, right? So if you have a persistent memory, theoretically, we'll have like high bandwidth, low latency, of course, and then so that solves most of the disk writes and burst fashion problem. And combined with the morning sessions that we have in-memory compactions and all kinds of fancy techniques, that may actually solve the problems really beautifully. And for disk bandwidth inflation, of course, high bandwidth always helps. And the cool thing is that it's non-volatile, which means that something you put in there, for example, as a cache, or some in-memory structure that you want to keep in the future, something bad happens, you can pick it up. You don't need to redo all the stuff over and over again. And the last one is data format changing. Consider this: if you're trying to do persistency on byte addressable device and put them back after a power outage or something, we can actually eliminate some of those format changings when you do persistency. We probably need very, very large HDDs to do persistency for a longer time, but for short term, like maybe weeks and days that you can hold into those persistent memory, you can do persistency there. That is a huge benefit. Right, so here is a little summary about where this persistency memory actually fits into our current storage stack. On the left side is what we have the current CPU, memory, and NAND SSDs and HDDs. The typical latency for DRAM, as I said, is about 100 nanoseconds or so, and it's like the fastest SSD you can have, 20 about or so microseconds. So there's about like several hundreds of times differences. So what we call the performance gap. Now, if you plug in the persistence memory, where performance is right between the DRAM and very close to the DRAM, and it has persistency as a plus. So that is something we can consider in the future that may actually help HBase to overcome some of the problems we currently have. Okay, so that given, we have done some experiment with the bucket cache on the HBase. Seems there's a lot of sessions on bucket cache though, because it's really easy, right? And it's very easy to plug and play and stuff. So the block graph shows how we actually did the job. We have put the bucket cache onto the persistent memory part, so that you have a LR cache on a regular DRAM with your regular JVM heap, and then the bucket cache looks very similar to what you have in off-heap cache, and it's on persistent memory. So what we did is like introduce a new I/O engine inside the bucket cache, and then for the native like allocations and operations for the native memory, we used the pmap.io implementation. Okay, and so the experiment was taken on a emulator platform where we can actually tweak the latency for the persistent part of the memory so that we can observe different behaviors. And we really focus on the performance impact. So we're not really taking into account of like how this persistency will help. Because to utilize persistency, there's a lot of code change in like all the stacks, like not only in HBase, but in other places as well. So a basic setup for the experiment, we're using the snapshot version for HBase, YCSB 0.6, Hadoop, relatively late version, and we preload the table to some size that cannot fix into the memory. And like default settings, 10 fields, 100 bytes per row, per field. And we're doing the YCSB Workload C, 100% read and throttled without any tweak on the distribution, so totally random. And all the measurements we are taken is after the bucket cache is fully filled. And for the experiment, we have many runs. So the baseline is where we only have a LR cache in the DRAM, and that's it. And for the persistent memory runs, we keep that same amount of LR cache, which is relatively small, and then we give an extra size of bucket cache on top of that, on persistent memory. And based on different sizes, we like to see how much that will give you performance. And we measure the throughput and latency impact on that. All right. OK. So first slide for result. In this graph, we're seeing that we're giving normalized results. So they are not absolute values. They're just speedups. For baseline is 1. And if we have more throughput, we'll just divide them against the baseline and show the differences here. So with the actual size of bucket cache from like 10% to 100%, what you can observe is about like an extra 5x performance you can get against the baseline. And you see the curve looks like the more cache hit ratio you can get, the better performance can have. Consider this. We are doing totally random reads. And normally in the real life, your read will be skewed. So the cache hit ratio somehow will be a little bit better than the size ratio here. OK, so let's see the latency part. So of course, latency reduced and is following the same trend. And from no bucket cache extra to 100% bucket cache, we reduced the latency by about 95 percentile latency by about 55%. So given this, that you want better SLAs and everything, plug it in, and this just works. So yeah, it's just really nice. OK, so some quick summary here. For a simple test, we see significant performance improvement on this one, and throughput-wise, latency-wise, and everything. What is really interesting is that this persistent memory that actually offers a whole bunch of new ideas or new possibilities that we haven't think about before. Maybe persistent on the memory so that you don't need to do over and over of those compactions again, and writing more useful code than just taking those in-memory structures, saving spaces, bring things back more wisely and stuff. No more format changing overhead. That's just really cool because consider this: if you can put something on your Java heap, then you don't need to do this off-heap buffers or something. Then just be there, and that is always there. Fantastic. And faster recovery for emergencies and stuff. OK, so yeah, that's mostly all I have. And our work has been joined with Anoop and Ram sitting there. Thanks, guys. We have some preliminary code changes probably can share with the community somewhere in the future.